Muy bien, buenos días a todos los presentes y a todos los que nos están siguiendo por internet, por indicaciones del director de la revista. Dice que como estamos en España, empezamos un poco en español y luego la presentación más científica será en inglés y la conferencia del profesor Souplet será también en inglés. Pero bueno, pues quería decir eso. En primer lugar, me gustaría presentar a las personas que están conmigo en la mesa. Eh, por deferencia al invitado, en primer lugar, al profesor Philippe Souplet, que es de la Universidad de la Sorbonne en París y al cual le quiero agradecer que haya aceptado esta invitación para uno de los eventos que para nosotros es más importante, indudablemente la conferencia más importante del año escolar en nuestra facultad. A mi izquierda, yo creo que le conocemos todos, pero por si acaso es el profesor Marco Castrillón, que no solamente es profesor del Departamento de Álgebra, Geometría y Topología de la Facultad de Ciencias Matemáticas de la Universidad Complutense, sino que es el director de la revista Matemática Complutense, y al cual le quiero agradecer también la organización de esta conferencia, que es el que ha llevado fundamentalmente el peso de la organización, con lo cual muchísimas gracias por esa presentación. Más a mi izquierda también está el profesor Aníbal Rodríguez, que es del Departamento de Análisis Matemático y Matemática Aplicada de la Facultad también de Ciencias Matemáticas de la Complutense, que le quiero agradecer también el haber propuesto al profesor Philippe Souplet y que va a ser el encargado de hacer una introducción más en profundidad de las líneas fundamentales del profesor Philippe Souplet. Antes de empezar, pues quiero recalcar un poco la importancia de esta conferencia Santaló. Para nosotros todos los años marca un hito, en teoría es un principio simbólico de lo que es el año en cuestión de investigación, el curso en cuestión de investigación, y por lo tanto siempre queremos darle la mayor importancia, el máximo realce posible, puesto que para nosotros es realmente importante. Junto con esta conferencia no podemos disociar también el de la revista Matemática Complutense, que es una revista que ya desde hace muchos años pues goza de un gran prestigio y de una gran calidad entre las revistas científicas. Es una revista propia, es una revista que actualmente está siendo editada por la editorial Springer. Yo creo que en los últimos años ha sido tremendamente beneficioso la colaboración con la editorial Springer y tenemos desde la facultad el absoluto propósito de continuar con esta línea editorial, porque creo que es la que va a garantizar el que continúe teniendo la calidad que actualmente posee y que sobre todo pues en el futuro podamos incrementarla. Por lo tanto, también quería decir esa cuestión y esa relación tan estrecha que tiene con la revista Matemática. Por otro lado, pues bueno, el profesor Philippe Souplet pues nos honra con su presencia. Es un gran investigador de una gran universidad, es un profesor cuyas líneas de investigación son fundamentalmente el análisis cualitativo de las ecuaciones diferenciales en derivadas parciales, el análisis funcional y la matemática aplicada, y que sobre esos aspectos pues tiene, entre otras cosas, 2 libros y más de 100 publicaciones en las revistas especializadas más importantes de dichas áreas. Yo creo que la conferencia que va a dar hoy pues es una conferencia que nos va a deleitar a todos y que es y por lo tanto le quiero agradecer una vez más su presencia aquí. Y ya para una presentación del acto desde el director de la revista Matemática, el profesor Marco Castrillón, y posteriormente una presentación más en profundidad de nuestro invitado, pues voy a pasar la palabra al profesor Marco Castrillón cuando quiera.
Pues muchas gracias. Muchas gracias. Muchas gracias, señor decano, y buenos días. Muchas gracias también por la presencia de todos y todas que estáis aquí, el equipo de canal, miembros de la facultad, profesores, colegas, estudiantes y en particular mis compañeros en el comité de la revista. También el profesor Arrieta aquí, antiguo director de la revista. Muchas gracias a todos los directores anteriores a mí. Les debo el haber creado esta, como ha dicho el decano, pues esta gran obra que es científica y que es muy bella. Tan bello como el día de hoy, que es la Conferencia Santaló, una de las actividades más preciosas y más interesantes de la revista, en la que publicamos grandes obras, pero hoy tenemos la oportunidad de tener en carne y hueso un conferenciante de primera línea como es el profesor Philippe Souplet. Pues esta reunión de hoy, tan bonita y tan llamativa y como buen comienzo de curso, bueno, el curso comenzó oficialmente ayer, yo creo, porque fue la apertura oficial del curso, o sea que no vamos tan, llevamos 3 semanas o 4 de clases, pero no vamos tan desajustados. Bueno, pues ha sido gracias al trabajo de mucha gente en el comité editorial con su apoyo continuo, el decanato, en especial nuestro señor decano, el personal de administración y servicios, muchos profesores con los que siempre he podido contar con su apoyo incondicional para el trabajo de esta revista. O sea que a toda esta gente muchas gracias. También, desde luego, quiero agradecer al profesor Philippe, que nos entiende perfectamente porque habla español maravillosamente. Y nada, muchas gracias. Merci bien, Philippe, pour être venu chez nous et chez toi maintenant aussi. Alors,
muchas gracias.
Merci bien. Y poco más que decir que vamos a disfrutar, yo creo que de una charla muy interesante. And I think that I'm going to switch now into English because I think that Professor Rodríguez Bernal is going to give some words about the work of Professor Souplet. So again, thank you very much to everyone. Thank you very much, Philippe. Professor Aníbal Rodríguez Bernal, whenever you want, please.
Thank you very much. So I think we are very proud and honored to have Philippe Souplet back in Complutense. Thank you very much for accepting the invitation. Okay. And so what to say about Philippe? It's difficult to compress more than 30 years of exceptional research in a few words, because we are not the core of this event is Philippe's talk. So I just would say that he developed an extraordinary career being an expert in analysis of PDEs, and he became very involved in understanding the mechanisms why, because of which make the solutions of nonlinear equations to cease to exist in finite time. There are several examples, several mechanisms that provide this. He has an extensive research activity on this. He has extraordinary knowledge on how these things work and why solutions in many different equations have a blow up, what is called blow up in finite time. His book with Pavel Quidner became one of the main references in the subject, where they compile a lot of results and produce results by themselves. And he was also involved in several of these different aspects of blowing up of solutions. And so here, as I repeat, we are very proud and honored to have him here and give us a talk in a general topic, which won't be too specialized. It's for general audience. And I think that's all I have to say. So thank you very much again for for being here with us, and it's your time now. Thank you very much.
Thank you. That's okay. Hello. Yeah, you can hear me apparently. So, hello everybody. That's a great pleasure and a great honor to be here in Madrid again. I think my first visit in Complutense was in the early, maybe more than 20 years ago, maybe almost 25 years ago. It's always a great pleasure to be back. Great honor to be the lecturer of this Santaló conference of this year. So I would like to give a kind of general talk about central topic in both complex analysis and partial differential equations, and maybe other fields, geometric measure theory and other things, of which I'm not an expert, but I will try to explain some connections. And so the central topic is the Liouville theorem. So let me try to give a kind of historical account. Of course, I have to be brief, and there are probably many things which I have to skip and maybe I'm not even aware of. Starting from the very classical and very well-known first result of this kind. So it's, let me check this pointer, yes, okay. So this theorem is apparently due to, it was announced by Joseph Liouville in the compte rendu de l'Académie des Sciences de Paris in 1844, only in a special case and without proof. And then about 2-3 weeks later, Cauchy, Augustin Cauchy, same journal, same compte rendu, came with a proof, almost essentially the current proof and essentially the complete result. So it just says, of course, that any bounded holomorphic function on the whole complex plane C is constant. And this is taught nowadays in every basic course on complex variable. And the proof nowadays is just to use Cauchy's integral formula, and it's quite an easy exercise once you have Cauchy formula at hand. And then there was probably some period of time where complex analysis methods were used to tackle many problems, including physical problems, engineering problems, maybe second half of the 19th century. And as far as mathematical results are concerned, it seems that the next step was about a half century later. Probably, okay, this has different names. Usually it's called the Picard theorem. Sometimes it's called also the Cauchy-Liouville theorem, it depends. And also the first published proof was due to Bochet, 1902, but it seems that Picard in his lectures in Collège de France or Sorbonne was teaching that much earlier, but it's not clear. We don't have written record. Okay, anyway, it says that any positive harmonic function on Rn is constant. A slightly weaker version is any bounded harmonic function on Rn is constant, but actually it's true if a one-sided bound is enough. So for instance, positive or negative or bounded for below, whatever, it's the same. And so the modern proof is probably due to Nelson in the 50s, 60s, but maybe it was not even new. It's a quite short proof. You just use the mean value formula for harmonic functions. By the mean value formula, it's quite easy to show that it has to be constant. Okay, and this again is taught in a basic PD course, maybe, I don't know, which third year or fourth year, I don't know. Okay, and in fact, so, okay, just to be precise, a harmonic function in this statement is just a C2 function which satisfies the Poisson equation, the Laplace-Poisson equation. So Laplacian is to 0, and Laplacian being, of course, the sum of all the second derivatives with respect to each variable. And this is true in any, this is in the, there are two improvements. This is just in C, so essentially in R2, and this is in any dimension, actually. And the second result contains the first one, because it's well known that any holomorphic function has harmonic functions as its real and imaginary parts. So you can deduce the first one from the second one. And in fact, you don't need so much regularity in the modern textbooks. You can just take distribution solutions, for instance, and it's well enough. And you have more abstract generalizations of harmonicity, okay, anyway. So these are the, let's say, the first two historical benchmarks. And now I'm going to try to see what kind of paths these ideas have taken through the 20th century and until now, to try to demonstrate how powerful these tools can be if they are suitably modified or adapted or smartly applied in certain ways. Okay, so to me, a generalization of, in this talk, generalization of Liouville, so I will call that a Liouville-type theorem for short, It's just more generally it's a statement about non-existence of solutions of a PDE in the whole space. Of course, the basic example is just Laplace equals 0, but you can think of any other PDE, take the whole space or maybe some large domain in some sense, and try to show that the solution, there are no solutions, or the solutions have to be, there are only few solutions, for instance, constants, or some restriction on the solutions. It's also called the rigidity theorem, or it can be a classification theorem. There are many instances of that. And sometimes you have to assume something on the solution, for instance, sign or growth or something. Okay, and hopefully you want to look at optimal assumptions which would guarantee such a non-existence statement. Okay, so this is the general line of the talk. Okay. So next, just let me outline. I had to make a selection of topics because there are so many directions. So I have chosen a few of them, partly because of their historical importance or mathematical importance, and partly because of my own taste or own, let's say, capacities. So let me start with the problem of minimal surfaces, so which is an extremely famous physical problem and engineering problem with very deep mathematical implications, starting even earlier than Cauchy with Lagrange. I will go back to that. And then connections with regularity theory for elliptic equations. Then I will move to this again, some part of the history, I would say, and then in the more modern period, I mean the last 40 years, I will turn to nonlinear elliptic equations, then nonlinear parabolic, and finally, maybe that's for my own taste, some Hamilton-Jacobi type equations. Okay, so that's kind of the program. So let me start with minimal surfaces. So of course there were some previous investigations by Euler before Lagrange, but Lagrange was the first to really point out the correct mathematical framework to treat such things. So just take a simple situation where you have a graph. So U is just a function over Rn, valued in R on the given bounded domain. So this, of course, if the function is not too bad, this defines a surface in Rn plus 1, an n-dimensional surface in n plus 1 dimensions. And you can, of course, define the area functionals, just the area of the surface or the perimeter. It's just this integral, which is well known, okay? And now a minimal surface, in fact, it's a restricted class of surfaces, it's just a graph. One maybe much more general, is a function U, which realizes for some prescribed boundary values G, the minimum of the area functional subjected to those boundary conditions. Of course, you have to assume some suitable smoothness, and this is a very big issue in modern theory. But you can just stay at the, let's say, informal level, or rough level at this stage. Okay, so what the main contribution of Lagrange, that was just two-dimensional, at least for physical reasons at the time, for concrete surfaces. And so he realized that any solution, any minimizer, if it exists and is regular enough, has to satisfy this elliptic equation, which is the very famous minimal surface equation. So divergence of grad U over the area density is 0. This is already a nonlinear equation. Surprisingly, it's even before Laplace equation, because Laplace is a little after Lagrange, and still it's a much more complicated object. It's already a very sophisticated object. Okay, and there were some preliminary researches of Euler, and so this is the prototypical Euler-Lagrange equation associated with the minimization problem. In fact, for any reasonable minimization problem, you can derive the optimality conditions, and this gives a PDE, which is in modern theorems called the Euler-Lagrange equation of the problem. So this is the Euler-Lagrange equation of the minimization of the area functional. Here, the boundary conditions can be added. So then in the 19th century, around 1850, there were a Belgian physicist named Plateau, who was not a mathematician, but who was a skilled experimentalist. And he designed the first experiments of soap film formation. So he just plunged a wire with a precise shape in a fluid, in a bath of soap, and then just dripping it out. He noticed that this produces soap films, and he probably realized that this had some very special shape, and some people, he or others, made a connection with the Lagrange equation. Okay. Then this was intensively studied by great mathematicians of the 19th century, essentially for 2 dimensions and by methods coming from complex analysis. So the big names, Riemann, Schwarz, Weierstrass. There were many special solutions, many computations, many beautiful things, but really of a computational nature, or more geometric, of course, with Riemann. And then the problem of solving, the question of solving the Plateau, so the so-called Plateau problem is just a Dirichlet problem for this PDE or for this midstream problem, which is at least formally equivalent. And so solving the Plateau problem means for a given contour, with under some assumptions on the contour G, show that there is at least, and if possible, a unique minimizer or a unique solution of the PDE. And this program was finally fulfilled under suitable geometric and topological assumptions on the contour in 2Ds by Douglas and Rado independently around 1930. And in turn, Douglas won the first Fields Medal for that. In 1936, he was awarded the first Fields Medal, shared with Alfors for some completely different things. And so this also some nice historical fact about the minimal surface equation. But so far, this was 2-dimensional, and this was connected with existence. Then, continuing the minimal surfaces problem, there were other investigations, most notably by Sergei Bernstein, Russian mathematician from, let's say, early 20th century. He lived until 1968. And one of his most famous, Bernstein is, of course, a fantastic mathematician with lots of contributions in many areas. For instance, the approximation problem, how to approximate a continuous function by polynomials, or so this Weierstrass-Bernstein approximation problem is extremely important, and he has contributions in also PDEs and many other fields, probability and so on. Great result on that is the Bernstein theorem. It says that any C2 graph minimizing solving the mean surface equation now we are on the whole of R2. So this is the first connection with the Liouville kind of questions. What happens if instead of considering a bounded contour, like in the Plateau problem, you want to understand what happens if you just send the wire at infinity? What happens if the domain becomes extremely large? Of course, mathematically, you want to work on the whole of R2. Physically, maybe it doesn't make sense, but maybe this might give some light, some hint on the initial problem. This was a very important intuition that enlarging the domain is not just a pure mathematical curiosity, but it can give you some deep insight on what's going to happen locally. Okay, so this was the idea of Bernstein. So he showed that any entire solution of the mean surface equation over R2 has to be a affine function. So the graph is just a plane in R3. Or in other words, more modern word, the level sets are are planes. Okay, are lines this time. Okay. So this is the very beautiful theorem. So it's already a kind of a non-linear theorem because it says that on the whole space, some PDE has only very few solutions, affine function in that case. And most notably, unlike the Laplace case, harmonic case, you don't need any growth assumption on U. No growth assumption is required in this problem. And this reflects, of course, the nonlinearity of the problem, because if you have harmonic functions without growth, as you know, you have a polynomial of arbitrary growth as harmonic functions. You can easily compute, it's well known, but you can compute by hand some polynomials of very high degree which are harmonic. So if you don't put any growth assumption, there is no way. But for the mean surface equation, it's not so. You don't need any assumption. And the proof, very interestingly, and this is a very modern feature, boils down to a linear problem, a linear elliptic PDE, but with non-constant coefficients and in non-divergence form. So this is an important concept. I will go back to this. This is the general form on a non-divergence elliptic equation with linear but with non-constant coefficients. So it's just a trace of some matrix. Positive definite if you want it to be elliptic. This is the definition of ellipticity times the Hessian matrix of the unknown. And so this is the general form. Okay, and so what is the connection? So so Bernstein theorem is a consequence of this generalized Liouville theorem, also mostly due to Bernstein, although Hopf also has some contribution on that. If the matrix function A of x is symmetric, positive definite for each point, you don't need any bound, just for each point it has to be positive definite, but you don't need uniformity of this. Then any bounded solution V, smooth bounded of this, is a constant. So this is a very beautiful but 2D generalization of the Cauchy-Liouville theorem, but with non-constant coefficients. And this is very important because when you want to treat nonlinear equation, the idea is linearize. But when you linearize, of course, the pay to price is that your linearized equation, the linear one, has some non-constant coefficients. This is normal. So okay, let's admit this. I just try to give some sketches of proof when it's not too long. So once you have the generalized Liouville theorem at hand, how do you prove Bernstein? I just sketch it. So first, something which was already known to Lagrange and to his contemporaries, you just rewrite the mean surface equation in non-divergence form. Okay, let me go back to it. So this is the mean surface. It's in divergence form, obviously. So if you just do this multivariable calculus exercise that you can ask your students in the second year, expand this, expand the derivatives. Okay, simple computation. Normally, a normal student should be able to do it after some time. And it's just 2D, right? Well, with 2D. In 3D doesn't work. This story is really 2D-dimensional. Okay, so you just compute and you have this. So you have the three partial derivatives with coefficients which are themselves nonlinear functions of the unknown. So very simple, very very symmetric, very aesthetic form. So this is also another form. A Lagrange from Lagrange. And then there is a miracle which happens, and this was the genius idea of Bernstein, although it looks quite elementary once you have it in front of you. You just you differentiate the equation in x and y, okay? And then you try to see what happens with inverse tangent of u sub x. And this is miraculous, it's all the same equation. This is incredible, but it works. Again, if you have, I would say, a slightly smarter student, you can ask them to do that too. Once you show the trick, it's just a matter of computation, okay? The computer is a little longer, but it's still less than one page. So you do it, and you see it's same. And so look at this equation, it's just of that form. The matrix A has entries, these are the diagonal entries, and this is the off-diagonal entry. And of course, if you do the determinant, you see it's positive everywhere, irrespective of the values of ux, uy. So it's positive definite everywhere. So it's an elliptic non-divergence equation of that form. So you just apply generalized Liouville theorem, and it says that, and of course, inverse tangent, also a fact known to second-year student, is a bounded function. It's between minus pi half and pi half. So it's by itself a bounded solution of that. and so it has to be bounded. So it has to be, it has to be constant because of generalized Liouville theorem. So it means that the gradient is constant, so U is affine, and that's it. So it's really a fantastic proof, which looks very elementary, but the genius idea is to introduce, and it's typical from the early work of Bernstein, computing very smart auxiliary functions, differentiate the PDE in various ways, and combine everything to. And these kind of elementary ideas have many variants up to now. Even now, you can, with more complicated auxiliary functions, you can do a lot of things in nonlinear problems. Okay, so this is one thing. Then, of course, remarks, okay, it's not true for larger than 3. There are counterexamples due to Hopf a little later. So the natural question for the rest of the century was, what happens in higher Ds? And then there was a major theory originating mostly from the Giorgi and then over very important mathematicians like Almgren, Simons, Bombieri, de Giorgi Giusti. It's a beautiful story, which becomes more complicated if you are happy with graphs, it's okay. But if you want to take non-graphical surfaces or more abstract definitions of a surface like measure theoretical like the Giorgi or Fleming-Federer geometric measure theory, it's becoming very complicated. And there are two issues, existence or non-existence for the Liouville problem, the Bernstein problem, and then regularity theory for the surface itself. And this is still a field which is still in progress. And it's extremely technical. I cannot, I'm not an expert on that. And so the main thing is that Bernstein theorem is true if and only if the dimension is no greater than 7. It's a magical number. So de Giorgi for n equal 3, Almgren for n equal 4, then Simons for n less than 7, and then fantastic counterexamples of Bombieri, de Giorgi Giusti, 1969, a very famous paper. And then of course this Liouville theorem, both, or especially this one, is related to the regularity theory for minimal surfaces with more abstract objects, which was initiated by de Giorgi and then continued up to now with this incredible paper of Almgren, 2,000 pages long, 2,000 pages, Almgren's paper, and then more recently Camillo de Lelis simplified it to a few, let's say, 100 pages, something like that, or 200 pages. Very complicated, very beautiful. Okay, so these are the counterparts of the Bernstein theorem. So let me go back to second topic. So now the important connection between Liouville theorems and regularity of solutions. In fact, this comes from minimal surfaces, but it's much too complicated to explain simple ideas. The connection between Liouville, Simons proved the Liouville theorem, and then de Giorgi and others use it to prove regularity, but it's extremely technical and abstract. So it's to understand these connections, it's better to consider simpler variational problems. So there is a famous, among the Hilbert problems, the 19th problem is the problem of regularity of minimizers for functionals coming from mechanics, for instance, so Dirichlet minimization, possibly vector valued, like in elasticity, for instance, it has to be vector valued. And the basic observation is that, okay, the PDE requires C2, usually, the Euler-Lagrange, but the minimization problem itself is already makes sense just in H1 or some Sorbonne space. This means a space where the weak or the distribution derivatives of the function, first order, have some integrability property. This is enough. So the question is already aware. Hilbert was very well aware of that, and even Riemann. But Riemann made a false claim because the theory of Lebesgue did not exist at the time. So Riemann thought he could show the regularity, but there was a gap because he was minimizing in C1, and C1 is not a complete space with respect to Lebesgue measure. And this is where Lebesgue finally solved it. Lebesgue and Hilbert solved it, at least for the Dirichlet problem. And the more generally for general functionals, it's not obvious at all if the solution of the corresponding PD, the critical points of the functional, which solve something like that, do they have to be smooth? To be C2, for instance, it's not clear, or even analytic. The question of Hilbert was about analyticity. So this is a big problem of Hilbert, and it was completely solved in the linear scalar, let's say scalar case, which means u is real valued. So then the equation has this form, like just general divergence form elliptic equation. So this is another very famous result of de Giorgi and then Nash and Moser, probably the most important theorem, one of the few most important theorems in PDEs the second half of the 20th century. So it says that it's more or less like Bernstein theorem, but when you want to go to 2D, to higher this, you have to add some assumption because of the counterexamples of Hopf. And so the assumptions are you need some uniformity. So you need the matrix to be bounded, let's say in a larger ball, positive definite, and the positive definite condition is uniform in X. You have to assume that means that the first eigenvalue of the matrix is uniformly positive over the domain. Okay, so this is the main assumption of those theorems. And then you have two parts. There is a deep connection with the Harnack inequality. Harnack inequality goes back to 19th century for harmonic functions. It's very well known also, basic fact. And this works for more general equations under this assumption. So de Giorgi Nash Moser proved that you have Harnack in subdomains. So the Harnack means the supremum of the for positive solutions, okay, for positive solutions. So how we are here we are talking with weak solutions. You can think of distribution solutions, for instance. That's mostly enough. Okay, so any positive weak solutions. So weak solutions need not be continuous a priori. They are H1, so the gradient is square integrable, okay, the weak gradient, okay? So it need not be continuous, so let's say almost everywhere positive solution. Study the Harnack, the supremum is controlled by the infimum with a constant independent of the solution. This is Harnack, okay, inside, in let's say a half ball, okay? And then this is the main fact. And then there are some easier things, techniques to go from Harnack to regularity. So with Harnack at hand, you can show that weak solutions are continuous or even Hölder continuous. There's a known trick to do that. The deeper part is the first one. Okay, so this is still you don't see Liouville, but I will go to Liouville the next slide because I'm starting from regularity. So this proof doesn't need Liouville. It's based on very sophisticated test functions or truncations or so-called Moser iterations. So it's more test function type arguments. And then once you know that, you can, especially Harnack, which is obtained like that way, you get then you get the following Liouville, generalized Liouville. So if the matrix is like before, any bounded weak solution in the whole or Rn has to be constant. So it's really Liouville, except that now you have the matrix has non-constant coefficients, and it has satisfied the previous assumptions uniformly on Rn. And the proof, okay, maybe I skip the proof, but I don't have so much time, but the proof is really very elementary when you have Harnack, just a small perturbation argument. Okay, so there are similar results for non-diverse equations. I mean, similar to that, and similar to, especially similar to de Giorgi Nash Moser. So de Giorgi Nash Moser works for non-divergence, but this was observed later by Krylov and Safonov, 79. Very different kind of arguments. And of course, if you go to physical problems like elasticity, scalar value is not enough. In elasticity, you have to consider vectors, or in fluids, you have to consider vectors. So this theorem is very beautiful, but it has limited applicability for many physical problems. So then the natural question was, can you go to higher dimension? And can you go to, can you go to vector case? Sorry, this was any dimension, but can you go to vector case? And the answer is no, at least in 3 dimensions. And these are a series of beautiful counterexamples in the 1970s and later by all these people, de Giorgi, de Chas, and Schwerak, and others. So for some systems which are close to important physical systems like elasticity. So you cannot hope that unless you put more assumptions. So this was done, for instance, by Giaquinta and Netchas. So this is the other way around. We showed, in the previous slide, we showed Liouville as a consequence of regularity. And now we introduce a very important idea, which actually comes from the Giorgi in minimal surface theory, but too complicated to explain, easier in that case. If you want to show regularity for a system like this, even nonlinear, elliptic but nonlinear, how can you use Liouville? So there is a strong connection, which was identified by Giaquinta and Netchas at 79. They say that, okay, under some technical assumptions, which I will not recall, assume that the Liouville property is true. So the Liouville means, in that instance, it's the assumption that any weak solution of your equation on the whole space, if the gradient is bounded, then it's affine. So it's a little bit like before, except that you, instead of having constants, you have first order condition. But it's almost the same, because for harmonic functions, you have that. If a harmonic function has a bounded gradient and is bounded, then it is affine. Okay, so a first order polynomial. This is vector valued, okay? And so Giaquinta and Netchas were able to show that if the Liouville property is true, then all weak solutions are smooth. Smooth, okay, there are various definitions of smoothness, but reasonably smooth. Okay, and let me show you the key idea, because it's used, it has many implications for what follows. So the key idea is rescaling technique or zooming technique, which was probably introduced by the Giorgi for the minimal surface problem 20 years earlier. And the proof goes like this. So it's a little more technical, but still, you see it can be contained on half slide. So the main point is to show Hölder continuity of the gradient. When you show basically solution is H1, so the gradient is just L2. So if you can show that it's actually continuous or even Hölder continuous, then you can self-improve and go to higher regularity if you want. But so the key point is that continuity of the gradient. So how you show that? You fix a point in the domain, so it's interior regularity, and you zoom. So you assume you have this local solution of this. You zoom like this. You define a rescale function just by taking the so the zooming is here in red is because you have R is very small, so this means that Y can be very large. So the equation becomes defined on a very big sequence of expanding balls like this. D is the distance of that point to the boundary, so this makes sense provided Y is no larger than D over R. Okay, so R goes to 0, so this goes to infinity. So you expand like this, the gradient is just easily computed, and then you send R to infinity. And you use the ellipticity assumption. So ellipticity gives you some a priori estimates, gives you compactness. This is a key idea to remember for the students. Ellipticity implies compactness, local compactness. Okay, so I can't go to details, but that's the idea. So it means that subsequence of your VR goes to some limit in L2, because okay, we had an H1. Actually, we have an H1 bound, no, an H2 bound. Sorry, by the so-called Cauchy-Liouville inequality. And this gives you an L2 bound for the grade for the. Okay, here I'm. Okay, maybe I'm. What's that? Okay, no, it's L2. Sorry, it's L2. Okay, L2 bound for V. Okay, so H1 bound for V implies L2 compactness for VR. Okay, and so you end up with something which satisfies the same equation. So why the same equation? Because okay, here probably I'm talking about the linear case. So I'm giving the proof in the linear, more in the linear case. So in the linear case, it's more like this. Okay, and then you end up with a solution on the same problem because of the linear structure. If it's nonlinear, you have to add something more, but it goes basically the same. And then the Liouville property implies that your gradient is constant because you V is the solution of your equation. And because of the so you apply the Liouville property, so the gradient is bounded by construction, okay, and then you apply Liouville, and this gives you that it's constant. So gradient is constant. If you go, the gradient of V is constant. So if you go back to U, you see that U has small oscillation in average on small balls. If you scale back from V to U, you will see that this means that let's say grad U has small average oscillations in small balls. And then there's a trick, more technical, based on the so-called Morel-Campanato spaces, or Morel-Campanato estimates, which are kind of weighted spaces, with local weight, which shows that if it has small average oscillation, then it has small, it is Hölder continuous. Okay, but the key, okay, this is a little more technical, but the key trick is to rescale like this, and then to pass to the limit by compactness and to end up with Liouville. And then, can you show the Liouville property? Because of course it's a conditional theorem. So yeah, you can show the Liouville property, but you had either in 2Ds for any dimension of the vector, but in based on two-dimensional space, or otherwise adding structural assumptions. So I have to speed up a little bit. Now I go to semilinear equations. So semilinear equations, the prototype is this, which has two names, the Yamabe equation or the Lane-Emden equation for different reasons. So it's very famous. And so I have to recall a few facts about functional analysis. So you have the so-called critical Sobolev exponent. So this is this number. You have the Sobolev embedding, which tells you that the space H1 in the whole in Rn is included in have better integrability properties, meaning that you can integrate the function itself up to ps plus 1, so this number 2n over n minus 2, and this is concretized by an inequality between the LQ norm of f and the L2 norm of the gradient. It's a very famous Sobolev inequality. Okay, and then you can see that this is the Euler-Lagrange equation of the minimization problem associated with this inequality. You can write it with a Lagrange multiplier, or you can just avoid Lagrange multiplier by some homogeneity argument. There are two ways, but the connection is like minimization like before, except that it becomes nonlinear because of the differences between the exponents here. So okay, so this is known as Lane-Emden. It comes from some physical models of self-gravitating gaseous stars, and the critical case is a very famous Yamabe problem, which comes from differential geometry, which amounts to showing that on any compact Riemannian manifold you can find a conformal metric, which means a metric which is multiplied by a positive function, whose scalar curvature becomes a constant. So it's important in relativity and in other fields, and I have experts here, so I don't want to see too stupid things, but okay, that's the idea. So this is notably initiated by Yamabe, and then the complete solution came out from the combination of works of Trüdinger, Aubin, and Schoen in the 70s, 80s. Okay, so just to give some motivation for that equation, because it looks, why do you study that? Okay, there are some good reasons for that, and also it's a prototype, the simplest possible nonlinear elliptic equation. Okay, so there are two very important Liouville theorems on that problem. The first one is Guida-Spruck 81, which has a tremendous number of applications. This equation has no positive classical solution in the whole space if and only if P is subcritical, less than the Sobolev number. Okay, the necessity is very easy. You can construct ODE solutions, for instance, either explicit or by phase place analysis. And the sufficiency is highly non-trivial, and I will give a few words. And then the critical case is even more involved. Then in that case you have solutions, but it is unique up to the natural invariance group of the equation, dilations and translations. You have only one solution, which is given explicitly by this. You can compute also. It's computable for as an exercise in any dimension. Okay, so it's called the Aubin-Talenti bubble because it can be deformed by it has some, let's say, bump shape, but playing with dilations you can resize it like keeping same norm or something like that. Okay, so it's called a bubble. So the proof goes just a few. It's very technical. I give some idea. Like in Bernstein seminal ideas, you differentiate the equation using this very efficient formula when you compute the Laplace of the gradient v square, this so-called Borchner identity or Lichner-Rovitz-Borchner identity. Can be done also on manifolds, but this is Euclidean. And then you compute, you have a lot of terms, and you apply it to some power of u, and then you test with v to some power of v plus a cutoff, times the cutoff. So it's a mess. You have dozens of terms. You integrate by parts many times, and then you gather everything carefully, and then you try to optimize with respect to the real parameters m and k, and it works. It's a miracle, but it works. Okay, so the proof was simplified by Bidault-Véron. It's more readable, or you can look at my book with Pavel Quittner. We have a relatively compact proof along those ideas. And the second theorem is quite different. Not maybe the original proof, but the modern proof is based on moving planes. So it's just reflection. You have a solution, you reflect it by reflection, okay? And you have a new solution solving the same equation because this has a good structure. And then you play with the maximum principle, trying to identify the two of them. And if you have enough invariance by reflections, at the end of the day, solution has to be a constant, so it is 0. That's the idea, but it's also technical because it's not so easy to show that you can really apply the maximum principle to compare the two solutions. Okay, so there are many variants of the moving planes by those people. Even now, it's still very active subject. So these are two Liouville theorems, and they each of them has very important applications. So maybe we started a 2:15. Have like 15 minutes. Is it okay? I don't want to abuse of your time, but I should be okay with 15 minutes. So what are applications of Guida-Sprague? Okay, application of Guida-Sprague. Just take the simplest case because it has many more, but take, for instance, the Dirichlet problem for the same equation but with a non-constant coefficient, and try to solve it, try to show there are positive classical solutions. There are variational methods for that. Sometimes you can modify so that it is no longer variational, so you still need these kind of things. But even if you apply variational methods, you don't get a priori estimates, and this can be a problem for many other things. So the advantage of using Liouville theorem here is that you end up with both a priori estimates and existence. So under this subcriticality assumption, and if A is uniformly positive and smooth enough, then there is a common bound for all possible solutions a priori, even without knowing existence. And from the bound, you can deduce existence of at least one positive classical solution. So let me explain a little bit more. The sketch of a proof is again like in Giaquinta and Echas. Maybe Giaquinta and Echas was a little too technical. This is maybe it's easier. So let's do it by contradiction. Assume that a slight difference. The Giaquinta and Echas wanted to prove regularity. Here we don't want to prove regularity. We want to prove a bound. But it's of course quite related. So the idea will be the same. You zoom, you rescale. So if this is not true, it means that there is a sequence of solutions u sub k and points. You are in the compact domain, so you can assume that it converges to something, up to a subsequence, such that the maximum of solution achieved at that point goes to infinity. So this just assume that this is not true. Okay. So what you do, you rescale or you renormalize. So you rescale by the maximum. So just scale it up to 1. Okay, and also you have to stretch the independent variable because otherwise it will not satisfy the same equation. So if you stretch like this with the correct power here, you do a simple computation of 2 lines. You see that it will solve the same equation except maybe that a of x will be a of something different. Okay, so it's very easy. Okay, so same equation, but now what we gain is that the solution scales is renormalized to 1. So it is bounded. And it cannot vanish. It cannot escape to 0 because it is stuck to be 1 somewhere. Okay, so now you do elliptic estimates again. So of course, for those who don't know elliptic estimates, this sounds a little mysterious, but it's a kind of a magic box that you can apply to any reasonable elliptic operator to say that if the right-hand side of the equation is bounded, then you have C2 bound, essentially, something like that. Not exactly that, but something like that. So if you have a bound on the right-hand side, then you have very nice estimates for the derivative of u up to second order. Okay. So this means that you have a lot of compactness because you have compact embeddings in L infinity, for instance. So it means at the end you can produce a limiting solution of an equation. But now look, this point xk goes to x0, lambda k goes to 0, and y for x fixed y, this goes to x0. So this means that at the end, the point is no longer variable, it's a constant. It's a constant value of the coefficient. So you end up basically up to this constant multiple. It's just your Liouville equation, this one. You go back to this equation, and now you are in a whole space. Why? Because when you stretch the variable, you magnify the domain. So there are two cases. Either x0 stays inside at finite distance for boundary, then you zoom to the entire space, or maybe you approach the boundary fast enough, and then you may end up in a half space. It's a slightly different case. So half case is important in such situations. So if it's the whole space, then you have a contradiction with Liouville-type theorem, because you have a positive solution, and the Guidasproc-Liouville told you that you have no such solution. Okay. So so you have to. Okay. So up to the half space case, we are done. So this proves a priori estimate. And once you have a priori estimate, there is a powerful machinery which is due to essentially to Lagrange out there, which tells you that you have a degree, a kind of degree, topological degree, which tells you that you can deform the problem provided you control something on the boundary, on the topological boundary of your space. It amounts essentially to proving a priori estimate. So you can do a homotopy to your problem, to a problem that you can solve at hand, and the problem at hand has at least a solution. So by homotopy, the orange problem also has at least a solution by degree consideration. So that's the idea. And so in that way, a priori estimates will imply classical solution existence. Okay, so again, this connection between Liouville and the key idea of rescaling or renormalizing or whatever is essential. So now we have the half space case. We need also the same. So this was, of course, tackled also by Guidasproc, and they showed that you have also Liouville for solution on the whole half space, even including the critical case. And this was a hint, a clue to something maybe more of different nature that could be true. And this was first exploited by Dancer. Okay, now there is a conjecture that the same should be true without any upper bound, upper assumption on P. Should be true for any P bigger than 1. So the full conjecture is not proved so far. It seems quite difficult, but there has been a series of consecutive results. So going back to Norman Dancer, then Alberto Farina. So they were able to improve the bound here. Actually, Farina implies that it's true for any P bigger than 1, provided the space dimension is less, at most 10. Strange number. Up to 10 dimensions, the conjecture is true. For bounded solutions, okay, you need boundedness. Here you don't need boundedness. So the conjecture is without boundedness. Okay. So for bounded solutions, the full conjecture was proved more recently by Chen Li and Zhao. And then we did some improvement more recently for solutions which are locally bounded in the normal direction. So they could still grow up at infinity in the xn direction, but so there are some more technical improvements, but so far it's not clear how to prove the full conjecture. Anyway, for the applications that I just mentioned, we are subcritical. So here, this is fine, and this was, of course, a complete proof by Guidasproc. Okay, now let's go to evolution problems, which is another fascinating topic. So let me consider the evolution associated with the previous problem, the evolutionary Yamabe problem, if you want to call it like that, or a kind of reaction diffusion problem. If P is 2, so it's quadratic, you can see this as a chemical model where you have a second order mass action chemical reaction, and it would produce this amount of energy, and the diffusion would try to scatter the energy away. Okay, so that's various physical interpretations of that. So there is a beautiful theorem of Pavel Quittner, quite recent, where he was, there was a long series of attempts before, for 50 years. He was able to finally show that the elliptic Liouville has exactly the same parabolic counterpart. So he proved that this equation has no entire solutions. Okay, sorry, there's a missing piece of information. Positive classical here means x in Rn and time t in R, everywhere. So everywhere in time and space, negative, positive times, and any x. So this is the assumption of the theorem. Of course, the domain is missing here. Okay, of course, this is true. Of course, the necessity is also clear because we have, for instance, stationary solutions when P is bigger than PS or equal. So the difficult part is to show that it's sufficient. So non-existence. Okay, so there are a series of gradual improvements until this recent result. Also, so then I will show how you can use this kind of Liouville theorems to have nice information on the solution of the parabolic equation in the domain, for instance. Okay, so this can be done a little bit like in Guidasprug, but with the parabolic Liouville as a tool. So you need also the half-space case for the same reasons as before, and this we did before with Polacek and Quittner up to let's say the useful limit PS. So the proof is quite complicated. I can just draw a few ideas. You need the so-called similarity variables, which were introduced by Giga and Cohn in their famous series of work in the 80s to study blow-up problems. So it's a change of variable which modifies the equation in a way that you get more compactness, essentially. You have also a nice energy, compact energy associated with this new variable. And then you have hard energy estimates with Vitali-type covering arguments. You have to work in some kind of covering of your domain. It's quite technical, but the idea is that similarity, energy. And then at the end, what you show is that if such a solution, such a solution would exist, it would have to converge in some sense after some appropriate renormalization, it would have to converge to a stationary solution. And this doesn't exist because then at the end you still apply the elliptic Liouville theorem. So it's the philosophy is elliptic Liouville implies parabolic Liouville. Doesn't always work, but in that case it was very successfully applied in the previous attempts like Bidault-Véron. It was not that kind of attempt. It was a purely test function technique, and it had some artificial limitations. Okay, so what you do with that? You have many applications now to study not only bounds, but also singularity and decay of the solutions, which is an interesting issue when you want to understand the qualitative behavior of the solutions. So this we did, in fact, before, at the time where the full conjecture about parabolic Liouville was not yet solved, but conditionally to the conjecture, we could derive those estimates. So for instance, solutions in a strip like that, this implies a universal bound for the initial blow-up and the final blow-up rate with this number, which is the scale invariant number for the equation. So it's and a nice aspect of that is that it's universal. Then if the solution is global, then you just remove the second factor, so you get this. Now if you have solution on a domain, if you don't put any boundary conditions, so purely local, you have the same estimate except that you have some price to pay. Instead of having, this is basically the distance to the time boundary of your strip, and this is the distance to the space boundary. And so if you take the whole thing, it's like a parabolic distance to the boundary of this cylinder, you have the estimate like this, and this is sharp. And omega can be anything, can be even non-smooth. If you just remove a point, then you have an estimate for point singularities. Okay. Or if you have a domain and it is smooth, and if you put, for instance, zero boundary condition on that, then you have no price to pay. You just take one, some constant. But constant then will come out depending on the domain, and you just have a temporal decay or blow-up rate. Okay, so there are some nice, I will explain basically the idea of the proof, which is a little bit different from the elliptic case. And you have some nice counterpart. Maybe I don't have time to explain, but this has lots of extensions. Elliptic, you can, for instance, a nice thing is if you only have Liouville for bounded solutions, from that you can define Liouville, you can deduce Liouville for all solutions. So it means that boundedness assumption in Liouville theorems, in nonlinear Liouville theorems, are not so important, unlike linear, because the nonlinearity will force you something without, in the best case, without assuming even a bound. Okay. It's also non-variational, so it applies to many other things. So let me explain. The idea is the same as Guidasprug, so you rescale. Now you do parabolic rescaling, but otherwise it's the same idea. The difficulty is that you have possibly singular solutions, for instance, in time. or in space, but at least in time, if you're interested in blow up, then you cannot rescale a single solution around its maximum because it might be unbounded and blow up. So you have to find another way. And the idea is to use a topological tool, which we developed in that paper with Peter Polacek and Pavel Quitner. Okay, I wrote it in the most general case. It's a nice exercise in general topology. The proof is just like a little bit like Bayes' lemma. It's not so far-reaching. The idea, if you have a function which will violate some estimate regarding the way it approaches it diverges when you approach a boundary. So assume this is violated for some k or for some sequence of k as you wish. Okay, this is what happens if you want to prove that bound by contradiction, like in the elliptic case. But the problem is that you don't have bounds. So the idea is that you can pick another sequence of points which will still violate in the same way, but moreover will not grow too fast around that point. In other words, okay, the black assumption is that if the solution is more singular than what you want, then this more singular behavior must also happen at points of quasi-maximum. It cannot be so wild. Maybe it will be wild somewhere, but there will be points. Of course, this kind of argument exists already in other important papers of Richard Schoen, for instance, in differential geometry. It's not a totally new idea, but maybe the way it is written here is very flexible. You can use it in many different frameworks. But then you can pick other points where this happens, but it's almost maximum points. Maybe not maximum, but almost maximum. So it means that you can have the compactness business working because it will not be too wild around those points. And at the end, you end up with a positive solution, not on the elliptic equation, but the parabolic equation, and you end up by contradiction like before. Okay, probably I don't have too much time, maybe in 3 minutes, Hamilton-Jacobi. So with the same equation, but with gradient now. So it comes out from quadratic control. You have a dynamical stochastic control problem like this. This is Brownian motion. This is just a control acting on the velocity. And the final reward is connected with the PDE. So U0 is the initial data of the PDE. And so the final, so U0 corresponds in the control problem to a space distribution of rewards, which means that at the given time horizon that you fix, call it T, if you don't exceed the domain, if the stochastic process does not exit the domain before that time, then you have some gain, which is the value of U0 at the point where you get at that time. Otherwise, you get nothing. So you have a control, of course, because you need energy to drive the cost of the control. So cost of control is that. So you have this difference, and you want to optimize it. And the value function of the game, of the stochastic control problem, is the conditioned expectation of the process conditioned by the initial position, and of course optimize over all possible admissible controls. Okay, and the magic theorem of Barl and others is that the value function is the unique solution of the PDE, and you have to work with the so-called viscosity solution theory, which is a little technical, but it's just a kind of weak solution. Okay, so the value function of your control problem, minimizing in expectation value this, is the solution of the PDE. This is the connection. Okay, and then you have Liouville for that. Okay, there are basic peak features. You have finite time blow up, but that only the gradient blows up, not the solution itself. You can continue after blow up as a weak solution, like explained in the previous slide, but then you have understand the boundary conditions in a viscosity sense, which is a very weak sense, which might not be zero in the classical sense. It's a little strange, but the way the theory makes it is like this. And then you can have singularities which appear at the time. Of course, you start from something smooth. U0 initially is smooth, and then you can lose smoothness like this, and then you can continue as a weak solution. But the problem with those solutions is that they can lose boundary conditions in the classical sense, as I said, and this happens by singularities on the gradient on the boundary, and so first the gradient becomes infinite on the boundary, and then you detach, and you may lose a boundary condition in the classical sense. Okay, so there are many basic results on that. You can produce, for instance, single point singularities. So up to this is final time, first time appearance of infinite gradient. So there is one point, and away from this point, the gradient is finite. Okay, you want to understand the shape of singularities. So if you magnify with your favorite magnifying glass like before, because you are on the boundary, so you are typically in the half space case that we discussed before, because interior points cannot happen because inside you are smooth. It's only on the boundary. And if you look at the control problem, you have some heuristic explanation for that. And so this is the limiting problem. You just drop the time derivative. For some reason, you can drop the time derivative, and you have just this very simple looking problem. And there are two important Liouville theorems for that. The first one is due to Pierre-Louis Lyons for the whole space case. So this is not exactly, then you just take the equation, the whole space. So the whole space case, only constant solutions. You don't need any assumption, just regularity. Okay. Now in the half space, which you need to study the singularities of the previous problem, it's a more recent result that we got. In super quadratic case, which is the more interesting from the point of view of control theory, then you have a classification of solution. Any solution has to be one-dimensional. So it's a different kind of Liouville theorem. It's classification or rigidity. But it has to be very rigid. It has to be 1D. And 1D solution, of course, you can compute. This just becomes the second derivative, and this is first derivative. So it's another very simple exercise for your students. You can compute explicitly also. You just integrate twice, and you get explicitly solution 1D, and it's very useful then. And so with this, that's my last slide, essentially. So with this theorem, when you magnify the solution near a singular point, you can show that the gradient behaves like this, like a negative power of the distance of the boundary, like in the picture. If you look only in the normal direction, take a flat boundary just to make things easier, and look how you smooth out when you move inside the domain orthogonally to the boundary. It goes like this, and this is sharp. Okay, and the constant you can compute exactly. This is a constant which comes from the ODE. Okay, and then if you look tangentially, then it's more complicated. Tangentially, the Liouville theorem implies that it has to be more singular. So the way it's more needle shaped in the x direction than in the y direction. Of course, here I plot not the gradient, but if you plot the gradient, you will see this. And in some cases, we can compute the exact profile in the tangential direction, but not by Liouville theorem, by more complicated arguments. And then last application of Liouville, you can show that the equation. So here I have rewritten the same equation, but essentially in 2D, and in local coordinates, I can rewrite it as normal and tangential derivatives in 2D, just in local coordinates, or I can redefine the normal and tangential vector field locally, and it looks like this. And Liouville implies that the leading asymptotics will be given by this, just dropping the time and tangential derivatives. This doesn't mean that the equation becomes trivial, although it's ODE, because it means that if you want to capture all the tangential features, it is very delicate. It's very unstable because the main asymptotics is a normal one, but still the tangential mechanism exists, and if you want to capture it, it's more delicate. But still, Liouville will tell you this. And there are analogous results for other equations. I don't have time. You can also have nice classification about the loss of boundary conditions by using Liouville, but I don't have time either. I want to conclude with some overrated problems which I obviously could not touch, and where some rigidity or nonlinear Liouville-type theorems have proved extremely important and efficient in the past 30 years. Of course, first Navier-Stokes, still unsolved, but some, as you know, Loret proposed a way of possibly getting a blow-up solution for Navier-Stokes a long time ago, and this was ruled out. Those special so-called self-similar solutions of Loret were ruled out in some famous papers of Netchas and his students about 30 years ago. And then there are more work conducted with Liouville more recently. Now KDV, also for waves in shallow waters, has nice rigidity nonlinear to Liouville-type theorems from famous work of Martel and Merle. Even more famous, the study of Ricci flow by Hamilton and Perelman in relation to the Poincaré conjecture, when you want to rule out certain possible scenario of non-topological equivalents connected by some solution of Ricci flow, you have at some point to rule them out by using some very far-reaching Liouville-type theorems or rigidity, and also nonlinear wave equations, probably many others, harmonic maps, and many things. So I had to restrict myself to some selected topics, and I thank you very much for your attention.
Thank you very much, Philippe. So I don't know if we have, some time for a question or remark.
Yeah.
Let me see if we have the microphone, because otherwise, yeah, thank you so much.
Somehow the homogeneity in the equation plays essential role in the zooming procedure. Do there exist this kind of results for, say, fully nonlinear equations, something which is not semi-linear at least?
Yeah. For instance, many of those examples which I gave have counterparts for more complicated operators like the Pucci operator, not fully nonlinear. So, but fully nonlinear can have some scaling invariance. What is very unstable is the Liouville property. If you perturb the equation a little bit, you may lose the Liouville property in the whole space. So it means that you need some kind of homogeneity, or okay, we have some non-homogeneous versions of that, but it's quite restricted. Now, when you want to apply it, you have more freedom because you are magnifying, so you are rescaling. So all the, let's say, second or higher order terms will scale out in the process, and you can still use it because the limiting object might be homogeneous, although the initial was not completely homogeneous. And even though it's not homogeneous, you can do, it's a more recent work that was done, you can still, there is a way of rescaling. It cannot be widely oscillatory, but you can accommodate some logarithmic factors, or including positive, negative power with oscillations, and still keep some features of the rescaling procedures, ending up with something which is not necessarily homogeneous, provided, assuming, of course, that you have some Liouville property. So it is at the same time, let's say, the Liouville property is not very stable, but the applications are quite robust, I would say. Gracias.